for this experiment, I'm imagining that we have two masses made of unknown materials. Using the laboratory balance, we determine the mass of each of the two unknown metal cylinders and record these values of M in data table 1. So I think what I ought to do is take this laboratory data table and kind of copy it into good old Excel. And here it is, data table 1, data table 2, data table 3, calculations, table 1, table 2, table 3. And we're going to say that we measured the masses to be 71.65 grams and 65.57 grams. The next part says, place a clamp on a laboratory table and screw a threaded rod in the clamp. Okay, so here is the rod and the clamp right around here. It says the laboratory balance has a hole in its base designed to support the balance above the table. So I would guess that's somewhere around here in the diagram. It says slip the rod into the hole at the base of the laboratory balance and adjust the height of the balance far enough above the table to allow room for the 1000 milliliter beaker under the balance. Fill the beaker about 3/4 full of water. Tie a piece of light string around one of the unknowns and suspend it from one of the slots in the left arm underneath the balance. Determine the apparent mass with the unknown suspended completely below the surface of the water. Be sure that the unknown is neither touching the side of the beaker nor in any way supported other than by the string. Record the mass reading of the balance as M1 in data table 1. So we will pretend we have done this, and we've got for the first mass 65.21 grams, and for the second mass 56.92 grams. Repeat steps 1 through 3 for the second unknown. I've already done that. Step 5. From Appendix 2, obtain the known standard gravity of the metals of which the unknowns are made, and record those values in data table 1. I don't think I have given you Appendix 2. I apologize for that. But the first metal is lead, and the second metal is iron. And if you look at table 9.1 of your book on page 284, you'll find lead has a density of 11.3 times 10 to the third kilograms per meter cubed, and iron has a density of 7.86 times 10 to the third kilograms per meter cubed. However, we're going to repeat that in terms of standard gravity, which is the ratio of this guy's density to that of water at, I think, 15 degrees Celsius. And this one, well, it's just like basically multiply this by 1,000 kilograms per meter cubed or grams per centimeter cubed. I will mention, though, that I guess the lab manual used a slightly different value for that of iron, so I'm going to go ahead and change this to a 7.85. Calculations. I'm going to skip the calculations. I want you guys to do that part for yourselves. But for part 2, experimental procedure, object with density less than water, we're going to start by using the laboratory balance to determine the mass of the cork and record it as M in data table 2. So for that situation, you would put the cork on top of the scale and then read these numbers. Now, this would probably measure to about the 10th of a gram. They actually went hundredths of the gram, though, in the last two examples and in this example, where, you know what, this should be moved. Control X, Control V. This should say cork down here. and we have a mass of 0.00166. That's only 1.66 grams. So they have some kind of scale that is a little bit more sensitive to the triple beam balance that I was just looking at. Here is an example of such a laboratory balance. It says O House 311-00 dialogram in centogram 300 series balance. So it is getting down to that hundredth of a gram. So pretending that we have this cork and this highly sensitive balance, we get a mass of 1.66 grams or 0.00166 kilograms. I think though with the balance that we've got available at the school, um, we would probably we could use the digital balances to get M here, the actual mass. But to get M1 and M2, the masses from the balance while it's dunked under the water or fluid, we'd have to use the balance, we'd have to use a non-digital balance, which would end up having less precision. All right, back to the experimental procedure. Determine the apparent mass with the cork suspended in air and a sinker tied below submerged in water, as shown in figure 18.2a. Okay, so here we'll have the cork above the water and another mass below the water. What kind of mass was that? It just says sinker, so it doesn't specify what material the sinker is. So we do that, and the mass of the cork plus the weight of the cork plus the weight of the buoyed sinker comes out to measure as 0.06709 kilograms, 67.09 grams. So that is a lot more than the weight of the cork by itself, isn't it? Okay, but now we're going to 3. Determine the apparent mass with both the cork and the same sinker submerged in water, as shown in figure 18.2b. And we're going to record that value as M2. So here we're letting both the cork and the sinker be beneath the water, and the scale reads 56.99 grams. So it weighs a little bit less now with the cork being buoyed up. I will let you do the calculations table for the cork, and now we'll get to data table 3. Experimental procedure, liquid of unknown specific gravity. Use one of the unknown metal cylinders from the original procedure. Its mass m and its apparent mass in water have already been determined. Record those values in data table 3. Okay, so these don't really turn out to be input cells, do they? This is equal to the original mass of the lead and iron. I can just copy that over and copy that down, and it copies all 4 of those values. Okay. Part 2, using a very clean beaker, determine the apparent mass of the metal cylinder in alcohol. Record this as M sub L in data table 3. So that's going to look just like this experiment, except that instead of water in the beaker, we're going to have alcohol in the alcohol in the beaker. And we'll do that twice, once for each of the unknowns. Well, actually, once for the iron and once for the lead. And when we measure the reading of the scale, it says 66.50 grams for the lead and 0.05871 or 58.71 grams for the iron when it was dunked in the alcohol. Now, do we have well, let's go on to the next part of the experimental procedure. It says from Appendix 2, determine the known value of the specific gravity of alcohol and record it in Table 3. I don't think I've given you Appendix 2, but the specific gravity of alcohol is 793 grams per centimeter cubed, or 0.793 times that of, I'm sorry, it's 0.793 grams per centimeter cubed, or 7,930, no, 793 kilograms per meter cubed. Okay, so that is all of the data taken in this section. So I will leave the calculations to be figured out by